All right, so today we will be looking at the chapter of energetics. Before we start, you will need to have your data booklet with you because for this chapter, we will be using some parts of the data booklet. Example, like table 12 over here on bond energy, table 13 over here, which is on delta HF, as well as table 14 here, which is on delta HC combustion. And we also sometimes refer to table 16, which is on lattice energy. Yeah, that would be all for the data booklet part. So as mentioned before, enthalpy change is actually a measurement of the heat energy change during a reaction. So usually we cannot quantify the actual enthalpy, but what we are measuring is the change in the heat energy or the change in the energy of the system during a chemical reaction. So when we look at the enthalpy change, the general units is in kilojoules for reactions. If it's for reaction, it will be just kilojoules. But for specific enthalpy change, like for example, enthalpy change of combustion, enthalpy change of formation, enthalpy change of neutralization, then it will be kilojoules per mole, because in the definition, they do define 1 mole of something. Okay, but generally, if it's reaction, it will be just kilojoules. So we are measuring the energy changes that happens in the reactants and the product, and the difference between them will be the delta H. The greater the delta H of the substance is, the greater the enthalpy of the substance, that means the absolute enthalpy of the substance, the less stable it is. So as mentioned before, if you look at an energy profile diagram where you have your energy and you have your progress of reaction. So if you have a reactant starting here versus another reactant that starts over here, the reactant in red will actually the reactant in red has a greater energy or enthalpy and therefore is less stable compared to the reactant in blue, which has a lower enthalpy and is more stable. So after a reaction, be it is an exothermic or endothermic, it forms a product, and the difference between the energy of the reactant and the product will be the delta H. So there are a few delta H. Just take note that when we are talking about enthalpy change of reaction, okay, enthalpy change of reaction, the units is usually kilojoules. Can you cancel away the moles? It's usually kilojoules and is dependent on how the chemical equation is written. So if you have written it in this manner, N2 plus 3H2 to give me 2NH3, the calculated enthalpy could be minus 100. But if your friend has written it in another way, for example, in this manner, to form one more half N2 plus 3 over 2H2, you will find that correspondingly the delta H reaction will change according to the equation. So in this case, what we have done is that we multiplied by half to get the equation below, and therefore the delta H reaction value will also be half of the 100. Okay, so just take note, it's only more for delta H reaction, is dependent on how equation is written. So all these equations that we are going to go through is a thermochemical equation, and usually by default, thermochemical equation will show the reactants involved, the products involved, as well as the state symbols. So it is mandatory for you to include the state symbols of the reactants and products if it is a thermochemical equation. So I think we will skip this exo-endothermic reaction. I believe you understand. But I just need to emphasize to you that when you are looking at measuring a temperature change as a result of the reaction, the temperature change that you are measuring is always the surrounding temperature and not the system temperature. Okay, so if the reaction is an exothermic reaction, means the system is an exothermic reaction, you will see an increase in the temperature of the surrounding because the heat given out by the system is 100% taken in by the surrounding. We are assuming here 100% heat transfer, and there is no energy loss. It's 100% efficiency. So the surrounding experiences an increase in temperature as a result of the exothermic reaction that gives out heat. And generally, in an exothermic reaction, because net energy is given out in terms of heat, so the products will now therefore have lesser enthalpy values and they are more stable than the reactants. So a typical graph will be something like this. Whereas for an endothermic reaction, you will see that the system takes in heat from the surrounding, and as a result, the surrounding temperature decreases as it loses heat to the system. Okay, and in this case, because the system is taking heat from the surrounding or taking energy from the surrounding, the products will have a greater energy value than reactant. Okay. Now, so you need to know some common exothermic reaction and common endothermic reaction. So some of the common exothermic reaction that you must know will be combustion, neutralization, okay, these are by default exothermic. They will usually give out heat. All right, endothermic reactions. Some of the endothermic reactions that you need to know, for example, will be the dissolving of ammonium nitrate crystals in water that makes your instant ice pack, and also reactions like decomposition. If you are decomposing calcium carbonate, you'll be heating calcium carbonate strongly to form calcium oxide and CO2. So this type of reaction will be endothermic, usually because they're supplying energy. And also another type of reaction that's endothermic is photosynthesis. So photosynthesis, the plants will take in the energy from the sun, and therefore they will undergo its endothermic process. All right. So at the end of the day, we are calculating the first part of this topic is calculating delta H. After we calculate a delta H, which is the enthalpy change of a reaction, we will combine together with delta S, which is the entropy change of the reaction, to allow us to calculate delta G, which is the Gibbs free energy. So using the Gibbs free energy, we will be able to predict whether reaction is feasible or not. When we talk about feasible here, it means spontaneous. Whether the reaction will be spontaneous. So the most accurate way to determine if a reaction is spontaneous is to use delta G, which you will actually have to compute it using your enthalpy and entropy. Okay, so relying on delta H or delta S alone, it may not be an accurate prediction of the feasibility of a reaction. So delta G is the most accurate way, although generally most of the exothermic reaction tend to be more feasible than the endothermic reaction. Okay, that's a general trend. There is exothermic reactions tend to be more feasible, but if you want to be very sure, then we will have to calculate delta G, which is the Gibbs free energy. Now, why is exothermic reaction generally more feasible? Is because if you look at an exothermic reaction, the products are energetically more stable than reactants, and most of the chemical reaction proceeds towards greater stability. So because of the greater stability, so therefore they are likely to be more feasible or spontaneous. Okay, but again, always refer back to delta G. So feasible reaction doesn't mean that immediately you will see it happening, but it just means that reaction, once it's started, it will be able to sustain on its own without external energy input to keep it going. So example will be like rusting. Okay, just place an iron nail in water, walk away. Tomorrow you are back, or a few days you are back and has oxidized. So you didn't really need to do anything or provide any energy. It will continuously react on its own. Just like another spontaneous reaction will be an acid-base neutralization, whereby the moment you titrate your acid into your base, a reaction happens spontaneously without your energy input. Okay, comparatively, a non-spontaneous reaction will be something like decomposition. of a calcium carbonate. In order to decompose the calcium carbonate, you need to constantly provide heat to break down the compound, and therefore it is in a way non-spontaneous. You have to constantly supply energy. On its own, it does not break down naturally. Okay, now in this enthalpy change calculations, we often use a standard set of conditions, and this standard set of conditions is not STP. So just a quick recap, this standard set is not STP, but what we are looking at is we are looking at a pressure of 100 kilopascal and concentration of aqueous solution at 1 mole per dm cube. And even though temperature is usually not stated, but we will assume it to be 298 Kelvin. So if the reactions are carried out under standard conditions of 100 kilopascal, 1 mole per dm cube, and 298 Kelvin, then the delta H will carry on the symbol, the theta. So you have a delta H with a theta versus a delta H. The difference is that if you see the theta sign, it means that the reaction is conducted at standard conditions of 100 kilopascal, 1 mole per dm cube, and 298 Kelvin, whereas a delta H without a theta may not be carried out under, the reaction may not be carried out under the standard condition. So for data booklet wise, you'll find that bond energy, you don't really see the theta sign, but for delta H formation, for delta H combustion, you'll find that you'll have a theta sign here because they actually mentioned that it's carried out at 298 Kelvin and a pressure of 100 kilopascal. All right, now there are a few types of enthalpy changes. If you look at data booklet, you will see that there's delta H formation, there's delta H combustion on table 14. So what exactly are the delta H formation and combustion? So delta H formation is when 1 mole of compound. So we are looking at 1 mole. So therefore the units has a unit of kilojoules per mole. For this case, okay, 1 mole of compound is formed from elements. So make sure you are forming it from elements and under in their standard state. So the elements must be in their standard state. So for example, that's the state that that it exists in and is most stably found at standard conditions. So for example, the standard state of hydrogen will be a gas, not a liquid. The standard state of sodium will be solid and not liquid. So that's the state that they are found naturally at under standard condition in their most stable form. That's the meaning of standard states. So 1 mole of the compound is formed from the elements, and the elements must be in the standard state under a standard condition of 298 Kelvin and 100 kilopascal. So when you are writing the equation, the amount of compound must be 1. So as a result of that, sometimes in your equation, you may see fractions like this. You are not allowed to remove the fractions by multiplying by a value throughout, a multiple throughout to remove the fractions. Because if you do so, then it will no longer be 1 mole of sodium chloride. And therefore, it will not be representing an enthalpy change of formation because the formation is defined as forming 1 mole of compound from its elements under standard condition. Okay, so in the data booklet table 13, you will be able to see all the enthalpy change of formation of all the substances that you are encountering, but you'll find that you will not be able to find the enthalpy change of elements because the enthalpy change of formation of an element is 0. And why is it so? Because you cannot, when you form a hydrogen from a hydrogen itself, which is the element, there is no change at all. So as there's no change at all, so there will be no delta H formation value. There's no difference in the enthalpy of the product and the reactant. So enthalpy change of formation of all elements will be 0, and therefore you can't find them in this list. You got to remember it's 0. So elements here refers to things like aluminium, sodium, iron, oxygen, nitrogen, etc. Okay? So if what can we, so you can see that in the data booklet table, you'll find that delta HF values can be exothermic, can be endothermic. All right. It can be either depending on the formation of the product from the reactants, whether there's an increase in energy or decrease in energy. Okay. But generally, if the delta HF is more negative, that means the product form is more energetically stable compared to the reactant. Okay, now what do we do with all these delta HF values? We use these delta HF values to calculate the delta H of any reaction. So be it the reaction, be it whether it's a decomposition, be it whether it's a metal displacement or it's a redox reaction, we can calculate the enthalpy change of that reaction using the formation data. Okay, using the formation data of the reactants and product. So we will get the formation data from table 13 here, and we will apply this formula to calculate the enthalpy change of any reaction. So example, I could have a reaction like this, C2H4 gas plus H2 gas to give me C2H6 gas. So this is a reaction. It's an addition reaction. So to calculate the enthalpy change of this addition reaction, I can use formation data. Okay, so I can use the formation data that I can find here and find out what's the formation of the reactants, find out what's the formation of the products, and then apply the formula here, whereby the delta H reaction is the formation value of the products minus the formation value of the reactants. Okay, just take note that when we do this calculation, if there were 2 moles of C2H4, we will have to multiply 2 to the value in the data booklet, because the value in the data booklet is based on per mole. So if there were 2 moles of C2H4 in the equation, then we will have to multiply by 2 to the values when we sum up the values here. So example, let me see whether I can give you a better example. Okay, for example, let's say if I have CH4 burn in oxygen to give me CO2 plus 2H2O. So if you look at my equation, I need to put in the state symbol because it's a thermochemical equation. And then after I balance the equation, maybe I'll get something like this. So if I want to find out the enthalpy change of this reaction, which is a combustion reaction, I can use formation data. Okay, I can use a formation data to find out the enthalpy change of any reaction, example, a combustion. So what do I do with the data is that I will make use of the formula product minus reactant. And I will find out the enthalpy change of formation of CO2 and water times 2 minus of the enthalpy formation of CH4 plus oxygen. But because oxygen is an element, so the delta H formation is 0. So you can, put in 0 if you want, but if not, you can just leave it out. So the enthalpy change of this reaction will be CO2 formation plus water formation times 2. That will be the products minus the formation of methane. And that will, if I press my calculator, it will give me the delta H of the reaction. Okay, as long as I am using data from table 13, this will be the formula. Not only for delta H, you'll find that later for delta S and delta G, it's the same formula, products minus reactant, as long as you are using table 13. So, an example of a formation equation, as mentioned, let's give an example. For example, if I want to form ammonia, right? I form 1 mole of ammonia gas, okay? So it has to be formed from the elements. So I have to form it from nitrogen, and I have to form it from hydrogen gas. And balancing the equation, so this will be half, and this will be 3/2. So even though I do not like the fraction, I cannot multiply by 2 throughout because the formation is defined as forming 1 mole of compound. Okay, next we have enthalpy change of combustion, which you can see in table 14. So enthalpy change of combustion under standard condition, it means burning 1 mole of the substance in the standard state completely in excess oxygen under standard condition. So the amount of substance to burn must be 1 mole. So as a result, the enthalpy change may have a unit of kilojoules per mole. Now, this is in the substance must be in a standard state. And in this case, the substance can be a compound or can be an element. You burn it completely in the standard state under excess oxygen and you are under standard conditions. So it did not tell you that you definitely must get CO2 and water. Okay, CO2 and water is only for the case of carbons and hydrocarbons. But so if I have a case of burning hydrogen, so that will be my equation for enthalpy change of combustion of hydrogen gas. 1 mole of hydrogen burned in excess oxygen to give me the product. Okay, so this is an example of a combustion of an element. Okay, I can also have another combustion of another element. For example, let's say N. So I can burn nitrogen and I burn it in excess oxygen and I'll get NO2. So this must be 1 mole. And as a result of this will be 2 and this will be 2. So this is the enthalpy change of combustion of nitrogen under standard condition. So these are the equations for the elements. We can also have combustion of compounds. So example of compounds will be like, for example, an alcohol, which is a liquid being burned in excess oxygen. And under excess oxygen condition, I will get carbon dioxide and water molecules. So if you balance the equation, sorry, it will be 3/2. Okay, so that's the combustion, standard enthalpy change of combustion of a methanol. Okay, burn 1 mole in excess oxygen. Now, take note that even though we are doing combustion, the water that we are getting in the equation is usually in the liquid state because we are looking at standard conditions of 298 Kelvin and 100 kilopascal. So water at this temperature of 298 Kelvin and 100 kilopascal pressure condition will exist in liquid state. Even though combustion is a very hot exothermic process, but our measurement will be measured at the standard condition. Okay, now delta HC is always negative. Unlike your delta HF earlier, if you go back to the table, you can see delta HF can be positive, can be negative, depending on the stability. Delta HC is always exothermic. Okay, enthalpy change of combustion is always exothermic. Next, we have an enthalpy change. The next enthalpy change is neutralization. Now, enthalpy change of neutralization is defined as the energy change when 1 mole of water is formed from an acid-base neutralization under standard condition. So in this case, the focus is on the number of moles of water formed and not on the number of moles of acid or the number of moles of base. So its focus is on the number of moles of water formed. Okay, so depending on the equation, as you write your equation, that you have to keep this as 1 mole. Right. So if I have a sulfuric acid with NaOH equation, I cannot just happily write I cannot happily just write H2SO4 equals plus 2 NaOH equals to give me Na2SO4 equals plus 2 H2O liquid, because this is not actually an enthalpy change of neutralization. It should be based on per mole of water form. Okay, so I will have to halve the equation for the thermochemical equation. Now, enthalpy change of neutralization is always exothermic. Okay, enthalpy change of neutralization is always exothermic. And for usual strong acid strong base neutralization, they find that the enthalpy change is always about minus 57.3. Okay, but you will find that for weak acids and either you have a weak acid or you have a weak base or both are weak, you will find that for neutralization involving weak acids or weak base or both, you'll find that the enthalpy change of neutralization is less exothermic. Okay, so the nature of the acid will affect the enthalpy change of neutralization. When you have any of the component being weak, you'll find that your delta H is less exothermic. That means less heat is evolved during the neutralization to form 1 mole of water. Okay, and the reason is because since the weak acid and weak bases are only partially ionized, some of the energy that is given out during the neutralization reaction will be absorbed by the weak acid or the weak base to allow it to completely dissociate for the neutralization reaction. So the net energy given out or the net enthalpy given out will be lesser and it will be less exothermic. Okay, so how do we notice this less exothermic reaction? You'll find that if you do an acid-base neutralization, the delta T will be lesser for the weak acid or any reactions that involve weak acid or weak base in the titration. And as a result of a smaller delta T, so the calculated delta H will be also less exothermic. All right. So this is a test to distinguish a weak acid and strong acid. Okay, so we can always use this as a distinguish test for weak acids versus a strong acid. So if you have a weak acid versus a strong acid, what you can do is that you add in a fixed amount of base and you measure delta T. So the weak acid will show a smaller delta T because some of the heat energy evolved from the neutralization process is absorbed by the weak acid to allow it to further dissociate to complete the neutralization. So over in this example, okay, in the table, we have a strong acid, strong base. So you have a minus 57.3. So over here, we have a HCN is a weak acid. So we have a weak acid, strong base. You can see that it has a decrease in terms of exothermic, the amount of energy given out in the exothermic reaction. And next, we have this is a weak acid and this is a weak base. And you'll find that the amount of energy evolved during the neutralization is further reduced. So some students have done this for IA. So they look at a variety of weak acids and they note what is the effect of the Ka of the acid on the neutralization enthalpy. Okay. So at the end of the day, so now we learned 3 different enthalpy, formation, combustion, reaction, neutralization. Actually four types, right? So our main thing about this chapter first is to find delta H. There are many methods to find delta H. Okay, so a general view of the different delta H methods that we are going to learn will be firstly calorimetry. We can use calorimetry to do an experiment to find delta H. We can also use the formula and we calculate the delta H using delta HF value, as we have seen earlier. We can also use formula to calculate a delta H of a reaction by using delta HC values from the data booklet, again by using a formula. We can also find a delta H reaction by using bond energy that you have been doing in year 3, year 4. We can also find delta H by drawing Hess's law cycle. Or if you don't like the drawing, so we can use the Hess's law diagram. But most of the time, we don't like the diagram, okay, because it wastes a lot of time. So if there's other shorter method to do it, we use the shorter method. If not, we can manipulate the equation to find delta H. if we don't like to draw Hess's law cycle or energy cycle diagram. Now, for ionic compounds, there are two other delta H, which is the lattice energy. So we can use a Born-Haber cycle for that, for ionic compound. And one more, for ionic compound, there will be another delta H that we can calculate is by equation of delta H solution, hydration, and lattice energy. So there are so many ways to calculate delta H. All right, so we will cover each one. And after getting the delta H calculated, then we will calculate delta S and delta G. Okay, so first method is calorimetry. Okay, this calorimetry is often tested under experiment. So make sure you know, or graphical questions. So calorimetry is a technique that we do in the lab to measure temperature changes during a reaction. Okay, so what we are measuring is we are measuring change in temperature. And by recording the changes in temperature, we can calculate the enthalpy change of a reaction if we know the specific heat capacity. Okay, the specific heat capacity is the amount of heat required to raise the temperature of a substance per unit mass by 1 Kelvin. So for example, if I have water, then the specific heat capacity of water will be 4.18 joules. I will need 4.18 joules of energy to raise the temperature of 1 gram of water by a temperature of 1 Kelvin. So the specific heat capacity of water is 4.18 joules per gram per Kelvin. Sometimes you do not have a specific heat capacity. So specific heat capacity is shown by the small c. The small c here, the small c. Sometimes along the way, you may see the equation is something like that. Big C, capital C, delta T. So capital C is known as heat capacity. Not specific heat capacity, but heat capacity. And how do we get that? Capital C is equals to M times specific heat capacity. So by combining these two terms together, we call it heat capacity. That means the amount of energy needed to raise the temperature of the substance, not by per unit mass, the whole substance by 1 Kelvin. So capital C is seldom used. Okay, the heat capacity is seldom used, but just take note that the heat capacity is obtained by the mass times the specific heat capacity. Okay, so most of the time we are using specific heat capacity. So therefore, the formula that we're using is Q equals to MC delta T. Q is the amount of heat change. So the heat change can be heat absorbed, or the heat change can be the heat evolved. It could be both. So just take note, there is no sign for Q. So there's no such thing as negative Q. So what we will present is that is an absolute value. Okay, and we will just write down in our statement is a heat evolved or heat absorbed. If it's an exothermic reaction, there will be heat evolved rather than putting a negative sign on Q. Okay, so M here is the mass of the substance, C is the specific heat capacity of substance, and T is the temperature change. So there are a few ways to get the temperature change. You can measure the initial temperature and then measure the highest temperature or the lowest temperature that you encounter as the final temperature to get your delta T. So one way to get delta T is by using T final minus T initial. Okay, and take note that delta T again, we just take it as its absolute value. Now, in an experiment, this is what happens. This is your solution. In the solution, there are molecules. The molecules are the one that is reacting. So your molecules here, or your ions, are your system. They make up the system. Okay, but whenever you place a thermometer in, you are actually measuring the temperature of surrounding. Okay, it's the surrounding. So you are measuring the temperature of this surrounding liquid here. All right, so what we are doing here is that we are making an assumption that heat absorbed by the surrounding or heat lost by the surrounding is equals to the heat given out by the system or the heat lost by the system. So we are assuming 100% heat exchange, negligible heat loss, 100% efficiency. Okay, so take note of this. Now, next, I want you to see where you place the thermometer. So you place the thermometer in the surrounding, right? So when you place the thermometer in the surrounding, then you are measuring temperature of the surrounding. And the heat, and therefore, because the temperature belongs to the surrounding, the temperature change belongs to the surrounding. So therefore, the specific heat capacity should also be the surrounding specific heat capacity, which is water in this case, and the mass should also be the mass of the surrounding. It has to be consistent. Right? It has to be consistent because a most common mistake is that some students, they will actually use the mass as the mass of the reactant. The mass should be the mass of the surrounding. Okay, so because it has to be consistent. Since you are measuring temperature change of a surrounding, then everything should be with respect to that thing. So the specific heat capacity should also be the aqueous solution. The temperature is the aqueous solution. The mass should also be the mass of the aqueous solution. Okay. Now you'll find that nobody takes water to a measuring balance and measure the mass. So we will never measure the mass of liquid. So for liquids, what we always do is we measure volume. So in this case, we are assuming volume is equals to mass, and we will sub in the volume as the mass. So for example, if this is a 100 cm cube, we will assume that since this is 100 cm cube, the mass will be 100 grams, and we sub that into m. And we can make such an assumption because the density of water is 1 gram per cm cube. All right. So we are assuming that the solution is following the density of water. But most of the time, the solution is not water. It could be an aqueous acid, it could be an aqueous base, it could be an aqueous copper sulfate solution. So if that's the case, there's an assumption behind our calculation. We are assuming that the density of the aqueous solution or the aqueous acid is the same as the density of water. Okay, because we have no way to keep finding the density of so many liquid. Second thing is that the specific heat capacity that we are using here is also the specific heat capacity of water in the data booklet. So if you go to the data booklet, okay, let's look at the data booklet, table 2, you will find that there is this specific heat capacity of water here, right? And again, the solution is not water. It's an aqueous acid, it's either aqueous base or some aqueous metal ions. So therefore, there is another assumption in the calculation that the aqueous solution specific heat capacity is similar to that of water. All right, so with all those assumptions behind us, it allows us to do a calculation, but of course, at the same time, it brings about some inaccuracy. So this first part gives us Q, which is the heat of the reaction. Then next, we will substitute our Q into the formula, delta H over limiting reagent, to find out the enthalpy change of a reaction. So to find an enthalpy change of a reaction is usually by dividing the Q or the heat change by the number of moles of limiting reagent. Now, that's where the sign comes in. If the reaction is exothermic, you must put in negative. If the reaction is endothermic, then you must put in positive and carry it along with you. Okay. Now, most of the time, for most enthalpy change of calculation is based on moles of limiting reagent. However, if you are calculating delta H of neutralization, then the formula will be different. For delta H neutralization, the formula will be negative Q over number of moles of water. Okay? Q negative because neutralization is always exothermic. Number of moles of water is because the definition of neutralization is based on per mole of water form. All right. Now, is the number of moles of water always the same as the number of moles of limiting reagent? It may not be, it may be. So it depends on the equation. Okay. So example, let's look at an example where it is the enthalpy, where number of moles of water is limiting reagent. So if I have this equation, okay, firstly, can I write the equation like this if it's a neutralization? Okay, firstly, I can't write the equation like this if it's a neutralization because it should be based on per mole of water. So therefore, we will adjust it. And that's how we get the 1 mole of water. Now, if in this reaction, if the limiting reagent is this, then you can see that because of the mole ratio, by coincidence, because of the mole ratio, the number of moles of water is the same as the number of moles of limiting reagent, right? Because it's 1:1. Okay, but if the limiting reagent is this, and you'll find that the number of moles of water is not the same as the number of moles of limiting reagent in this case. Right? So then you have to calculate the moles of water from your limiting reagent. Okay? So next, let's look at this. Now, if we have an equation, I'm not sure whether I can find one. Let me find an equation that maybe can show you this part. Okay, so I have a displacement reaction. And if I do a displacement reaction, and if after my calculation, I found my delta H, okay, and in this reaction, this was the limiting reagent, okay, and I calculate my delta H and found that it's minus 100 by using Q divided by the number of moles of silver. All right, so what is the enthalpy change of this reaction? This reaction is minus 100 kilojoules per mole of limiting reagent, right? But because there was 2 moles of limiting reagent here, so therefore I will have to multiply by 2 for this reaction. So after if you calculate the amount of heat divided by number of moles of limiting reagent, you get the value. You'll find that is minus, let's say, 100 kilojoules per mole of limiting reagent. But so happen that the equation is not written in terms of per mole of limiting reagent, right? It's written in using 2 moles of your silver. Therefore, the enthalpy change of this reaction will have to be multiplied by 2. So it will be 200. Okay, so when will it be 100? It will be 100 if the equation was written in this manner. So if the equation was written in this manner, based on 1 mole of my limiting reagent, if silver is the limiting reagent, Okay, and the equation is written based on 1 mole of limiting reagent, then yes, for this reaction, the enthalpy change is minus 100. Remember, enthalpy change of reaction depends on how the equation is written. So if the equation is written in this manner, what we have done is that we have multiplied the green color equation by 2 to get the red color one. So therefore, the enthalpy will also have to be multiplied by 2 from minus 100 to minus 200. That is for enthalpy change of reaction. Okay? So I think later you will see some example on this. I think one of the example is something like that. Okay, I think you may see one of the example in one of this question here that you actually may have to multiply by 2, depending on the equation, the way it's written. Okay, so let's look at an example of how to solve the NC delta T. Okay, let's go through maybe 2-3 examples if we have time. So first is that now we have a combustion. We have an ethanol burned in a spirit lamp used to heat up the water for 5 minutes as shown. So the temperature of this amount of water, which consists of 500 grams, changes from so much to so much. So it changes from this. So from here, we can work out the delta T. From here, what we can see is that we see temperature increase, and therefore it's an exothermic reaction because temperature of surrounding increase. Okay, and the delta T will be equals to 34 minus 25, so 9 degrees Celsius. Okay, take note that even though my equation is Q equals to mc delta T, and the note says that delta T is in Kelvin, take note that delta T in degrees Celsius is the same as delta T in Kelvin. This is a very common mistake. Some students, after calculating the delta T in degrees Celsius, they will add 273 to change to Kelvin, which is wrong. Okay, delta T in degrees Celsius is the same as delta T in Kelvin. Okay, some students don't understand why. Because if you want to do a temperature calculation in Kelvin, then your temperature should both be converted to Kelvin, then you do a subtraction. So it will be, in this case, 25 degrees will be 25 plus 273. So the T1 initial should be 298. And the T final should be 34 plus 273. So it should be 307. Your delta T should be 307 minus 298, which is also again 9 Kelvin. So delta T in degrees Celsius is the same as delta T in Kelvin. There's no need to convert. All right. Okay, take note of this. So the temperature of the solution that I'm heating is water. Look at where your thermometer is. Thermometer is measuring water. Therefore, mass should be the mass of water. Heat capacity should be the heat capacity of water because delta T is the change in the temperature of the water. Right, so with that, we will find our Q first. Q is equals to M C. C is given delta T. So with your MC delta T, then you find out the Q, it will give you a roughly about 18810 joules. Then with that, in this case, we are doing combustion. In combustion, the limiting reagent is the fuel because air is all around us. Oxygen is definitely in excess. So we need to find out the moles of our limiting reagent. So the moles of the alcohol that is the fuel that we are burning is equals to the mass loss. The mass loss means the amount that is gone after burning divided by the MR of the fuel. Right? In this case, the fuel is ethanol. So the mass loss will be 0.950 over the MR of ethanol, which is about 46.08. So with that, we will find the moles of the fuel is about 0.0206 moles. All right, then delta H, remembering delta HC theta is an exothermic process. So the equation will be minus Q over number of limiting reagent, and therefore is equals to negative, carry a negative all the way with you, negative 18810 divided by 0.0206. So you get the enthalpy change of combustion per mole. And that's around negative 913 kilojoules per mole. I'm converting it back to kilojoules. Okay? In joules, it will be minus 912621 joules. But I'm converting it to kilojoules. Now, comment on this value. So after you finish your experiment, you got a value negative 913. That means giving out 913 kilojoules of energy. But the literature value is telling you that you should be giving up more energy, 1,371 kilojoules. And you are supposed to account why is there a difference. So there could be a few differences. Firstly, what are the, again, there will be heat loss to the surrounding. Besides heat loss to the surrounding, you will find that when we do our calculation, we are only assuming that the water is taking in the heat. We are assuming that this container or your calorimeter doesn't take in any heat. So you will find that the heat taken in by the calorimeter is not being accounted. Okay, to account for the heat taken in by the calorimeter, most of the time, you will have to do a calibration for the calorimeter. So heat taken in by calorimeter is not factored in. And also, you are assuming that there is a complete combustion, whereby all your fuel are all converted into CO2 and water. Okay, and next, you are also assuming that all the alcohol that you have lost all the alcohol mass change is equals to combustion, those alcohol burnt. So there is actually all the alcohol mass change due to combustion. So there is no evaporation loss. Okay, no alcohol loss via evaporation. Okay, so this is an example of combustion. Next, we will go to another example, which is on reaction. In this case, it's a neutralization. So I have NaOH mixed with HCl in the styrofoam cup. So in that cup, I will have some HCl, 250. Then I'll put in another 250 NaOH. So now I have 500 in the solution. And then I will put in a thermometer and measure the temperature change. Right? So therefore, please take note that the total volume is now 500, which is your M. So over here, the equation, it will be NaOH plus HCl to give me NaCl plus water. If you want, put in your state symbols. Right, so we find our temperature. So the temperature was at 20 degrees and it went up to 22.6. So telling us that this is a delta H exothermic reaction because temperature of surrounding increases. Okay, and the delta T in this case is 2.6 degrees Celsius, which is also 2.6 Kelvin. So Q is equals to MC delta T. So our M here is 500. C is 4.18, assuming it behaving as like a water. And our Q is, delta T is 2.6. So with that, we will have our heat as 5430 joules. Now, looking at the values here, 250 times 0.4 for the moles of NaOH, 250 times 0.4 for HCl. So they are equimolar. So therefore, either one of them, I can use either one to calculate limiting reagent. In this, sorry, not limiting reagent, I can use either one to calculate water, because the mole ratio of water is the same as the mole ratio of NaOH and HCl. So neutralization is defined by per mole of water. So first we find the number of moles of water, and that is 0.25 times 0.4. So our number of moles of water will be 0.1 mole. So then we calculate our delta H, which is neutralization at theta, is equal to negative Q over N water. So you have your negative 5430 over 0.100. Your answer first in joules per mole, which you can convert to kilojoules per mole. So the joules per mole, maybe you will get is about minus 54300 joules per mole. And if you convert to kilojoules, minus 54.3 kilojoules per mole. So it is negative. The negative sign has to be carried throughout, carried down all along, all the way in your calculation. Now, so given that this is a strong acid, strong base, I get 54.3 and I did not get usual 57.3 because heat loss, right? Heat loss in the reaction. So I'm assuming that all the heat is taken in by the thermometer and none by the styrofoam cup, and no heat loss to the air, right? And also another thing that we are assuming again is the specific heat capacity. Is this really water, or is this an acid and base? And also the density. Is this really water, so that the volume is really mass, you know? And also if you look at the reaction actually forms water. So this amount of water formed is not added to the 500, right? We are assuming that we are not including this to the total volume. So there are a lot of assumptions that we will have made. So you can write it down. Okay, there is no heat loss to the surrounding. The styrofoam cup does not absorb heat. Heat capacity of the acid base so the heat capacities of the reagents are the same as the water. All right, and etc. Okay. Now, what would the volume be? What would the value of the enthalpy change be if HCl is replaced by ethanoic acid? So you'll find that the value will be less exothermic than 54.3 kilojoules per mole. Okay, and the reason for the less exothermic enthalpy change is because energy will be absorbed by the weak acid to dissociate the weak acid fully to form ions. All right. Okay, so you can also repeat the same experiment. Instead of taking T initial, T final, you can repeat the same experiment, but recording every half a minute the temperature change over a period of time. So you can first put in your acid, for example, in the flask, in the styrofoam cup, and at exactly 2 minutes, then you put in the base. And then, because 2 minutes you are busy adding in the base, you're not able to record the temperature change. So you will start recording at 2.5 minutes and so on until you collect enough data. So what do you mean by enough data? We need to have enough data to get this cooling portion of the graph. Okay, so the first portion, the first few minutes, it is up to the first 1.5 minutes, it's just the temperature of the acid, so it's quite constant. The moment at 2 minutes you add in some base, the temperature may show increase. And then after a while, it starts to drop. So the point when it starts to drop is telling us that the reaction is completed. So the moment the temperature drops, it's telling us that reaction is completed already because it's dropping now. There's no more energy produced by the reaction. So we do not stop immediately when it's dropping. We will still collect a few more temperature as the temperature drops. We collect a few more temperature readings as the temperature drops. And the purpose of it is to draw a cooling curve. All right, so what do we do is that after we collected a few data of the temperature drop, what we will do is that we will extrapolate the cooling curve. So these are the regions where temperature drop. So from here, draw a line. From here, draw a best fit line. Okay, and the delta T is not the point where it cuts the y-axis. Please, the delta T is always mistaken as the point that it cuts the y-axis. It is not, okay? So the delta T, wait a minute, let's say, let me extend the y-axis. So please do not tell me this is the T max, okay? The delta T should be extrapolated to the time of mixing. So rather than matching it with the y-axis, make from the time of mixing 2 minutes, draw a vertical line upwards. Time of mixing 2 minutes, draw a vertical line upwards. The intersection is the maximum temperature that you should be getting if there were no heat loss. So extrapolate back to the time of mixing. Okay, and the initial temperature in this case, will be the values at the first 0.5 minutes here, and the maximum temperature will be the intersection, and you read off. So when you do such a method, when you plot a temperature time graph, you actually are trying to extrapolate to the time of mixing. And the fact of extrapolation is to account what would be the maximum temperature that you will get if there was no heat loss. So you're using this gradient, which is the rate of heat loss, to extrapolate back to the time of mixing, so that you'll find that if there was no heat loss following this rate of heat loss, this should be the maximum temperature that I will record. So you'll find that if from this graph you get 23.4, and you find that in your table there is no 23.4. You do not get 23.4, but when you extrapolate, you will be able to get a higher reading because you're factoring the rate of heat loss back into the experiment. Okay, so this graphical method to obtain the highest temperature is important for reaction that is occurring very slowly. All right, so when you have a solution that is reacting and is very slow, there will constant heat loss to the environment. So the extrapolate temperature will help to compensate the loss to the environment for slow reactions and for reactions whereby your thermometer is not sensitive. All right, so just a summarize of this part. Remember, Q is MC delta T. Q is always a positive number. So even if your delta T is a negative delta T, you present it as a positive number. Delta H of a reaction is always equals to Q over N. N can be limiting reagent. N can be number of moles of water, depending on whether you are doing delta H reaction or delta H neutralization. So for delta H reaction, after you have calculated, that is the value that you will get per mole of limiting reagent. So you go back to your equation and see in the equation how many moles of limiting reagent is written. And you will adjust the delta H value accordingly to how the equation is written. Okay, so example, if the reaction is written in this manner, you finish your calculation, since and your limiting reagent is A, then the delta H will be as follow, whatever you have calculated. But if the equation was something like this, then after you, and your limiting reagent is still A, after you have calculated is for per mole of A. Since your equation has 2 moles of A, you will have to multiply by 2. All right. Now, if a reaction is not 100% efficient, then how? If it's 100% efficient, heat of surrounding equals to heat of system, right? If it is not 100% efficient, then the heat of surrounding is always less than the system. It's always less because heat is always lost. So if it's not 100% efficient, then the value that your MC delta T is always smaller. So then what you do is you divide it by the efficiency to find the actual amount of heat given out. So let's say this is your Q of the surrounding, and you find it to be 100 kilojoules, and the process is only 80% efficient. So what is your Q of your system? Your Q of the system will be equals to 100 divided by 0.8. It should be larger. It should be more. The original system has given out more heat, but the surrounding took in only 80% of it. So if you want to find the Q of the system, to use the Q of the system to find delta H, then you will have to make it bigger. You have to factor in the loss. Okay? All right. Okay. I think we stop here. You can try these questions first on your own. I will write down the numerical value so that you can try first before we go through. Okay. So the numerical value for first one is 40 Kelvin. The numerical value for the second question is roughly about minus 359.6 kilojoules per mole. The answer for question 3 is this is per mole of zinc. Okay. And the next question is about minus 256.4 kilojoules per mole of magnesium. Okay, you can try exercise 1 first, then we will go through in class. If you cannot, whether you can get the answer or not, we'll go through in class. But these are the values so that you can check whether you're on the right track.